Hello everyone, in this video we're going to talk about Newton's law of cooling. So essentially what this is an exponential equation that allows us to determine how long it's going to take something to cool off to a desirable temperature, right? So if we think about, like in this example we're going to look at today in the video, about a soup or a stew or something that you're cooking that's at a certain temperature, but we want to serve it at a cooler temperature. We can, based on the initial temperature, the temperature we want to serve it, the room temperature, kind of see how long it's going to take us or how long we should wait to serve the meal. All right, so it states that for a cooling substance with initial temperature T sub O, so T sub O is our initial temperature, the temperature T after T minutes, lowercase t, can be modeled by the following equation. So we have capital T, so temperature after T minutes, is equal to T sub O, or our initial temperature, minus T sub R, which is our surrounding temperature or room temperature maybe, multiplied by E to the negative RT, where R is our cooling rate of the substance. T would be our time in minutes. And then plus T sub R, which we said a minute ago is our surrounding temperature. Okay, so let's look at an example here where we apply this formula, or Newton's law of cooling. It says the temperature of a pot of soup is 212 degrees Fahrenheit. Room temperature is currently 75 degrees Fahrenheit. And the cooling rate of the soup is R equals 0.051. How long will it take to cool off the soup to a serving temperature of 95 degrees Fahrenheit? So I'm just going to rewrite our equation here. So T equals T sub O minus T sub R times E to the negative RT plus T sub R. So I know that the temperature of a pot of soup is 212 degrees. So that is going to be my initial temperature, or T sub O. So I know that's 212. My surrounding temperature is 75. So this is going to be minus 75. We have E. My R value, or my cooling rate, is 0.051. So negative 0.051. We're trying to figure out how long it'll take to cool off the soup. So we don't know our lowercase t. And we have 75 here as well. So this 95 that we have is our serving temperature, which would be our capital T. So we can plug in 95 right there, okay? All right, now we can just go ahead and simplify. So we have 95 here. We do 212 minus 75, and that's gonna give us 137. We have E to the negative 0.051 T, and then plus 75. So let's move this 75 to the right side, or to the left side of the equation. So now we have 20 is equal to 137 e to the negative 0.051 t. Now we can divide both sides by 137. So 20 divided by 137, and that's going to give me 0.146, and it keeps on going in my calculator. I'm going to leave that in my calculator and kind of work through it from there. I'm just writing the rounded decimal on the screen so that we can see it. Okay, so now we have e to the negative 0.051 t. Now to get rid of that e, I'm going to take the ln of both sides. So ln of 0.146, or basically ln of what's in my calculator right now, equals ln of e to the negative 0.051 t. So the ln of e will cancel out. And I'm going to take ln of my previous answer in my calculator, and that's going to give me negative 1.924. Once again, I'm leaving the entire decimal in my calculator. Is now equal to negative 0.051 t. So now I can divide both sides by negative 0.051. So divide by negative 0.051. And it's going to tell me that t is equal to, or I guess t is approximately 37.73. So now remember, t is our time in minutes. So this is telling us approximately how long we need to wait for the soup to cool down to serving temperature. So if it's more than 37 minutes, let's play it safe and let's wait 38 minutes until we serve it. All right, and that's how you can use Newton's law of cooling.